Okay, so hi everyone. The title of my talk is VirtualBox is Collapsing, an end-day story. So as you may have already guessed, I'm going to talk about hypervisor exploitation. But first, a little bit of introduction. Who am I? My name is Luca Ginex. I'm a vulnerability researcher at Exodus Intelligence. And in my free time, I'm mostly interested in operating system and low-level exploitation. At exploiter.dev, you can find my personal blog, where I share some of the resources I do in my free time. The blog is quite new, so there are just a couple of blog posts talking about Linux exploitation, especially NDA exploited with a friend of mine. So if you're interested, go and check them out. You can also find me on X, Twitter, whatever you want to call it, as Luca Ginex, and also on GitHub with the same handle. So, as I told you previously, I'm going to talk about hypervisor exploitation. This is the agenda of the talk. We're going to start with some basic introduction to the some virtualization concepts we will need later for the talk. We're going to talk about emulated devices, so how hardware access is granted to guest operating systems in a virtualized environment. So we're going to talk about the trap and emulate technique, which is a generic technique to provide access for guest operating system to hardware that is present on the real machine. We're going to talk about the implementation of VirtualBox, which is the target I used for my research. In particular about the pluggable device manager, which is the manager of all the devices instantiated at boot time of the guest operating system. Then we're going to talk about also the emulated PCI bus where these devices are instantiated. Then we're going to talk about the E1000 Ethernet controller, because this is the target of my research and where the vulnerability lies, where we are going to talk about that later. And so we're going to see how packets are sent to this controller and eventually sent out to the network. We're going to talk only about the transmission side of this controller. Then we're going to talk about the root cause analysis of the vulnerability I decided to use. Since this was my first time taking a look at hypervisor exploitation, I decided to start with a known vulnerability without a public exploit available. It's an old vulnerability from 2019. So we're going to see the parsing logic of the E1000 Ethernet controller. We will see the integer underflow that happens thanks to the vulnerability, and how to leverage that to have a guest-to-host escape to the host operating system, Ring 3. Then we will have a couple of demos video about the exploitation. So stick with me, fasten your seatbelts, because it's going to be a long ride. But I assure you it's going to be pretty interesting. So I want to start my talk by analyzing this scheme. It's a simplified representation of the software stack we can find inside a traditional computer. We have the operating system, which is running at ring 0, and it is the owner of all the physical resources, CPU, memory, and also access to other devices. Then we have the processes, which runs in ring 3, and they ask the operating system the access to hardware devices in this case through an explicit API. So, for example, a send for packets, or an access to read-write memory controller. Here I've listed a couple of features that is worth remembering during the talk. So we have the processes in ring 3 that are completely isolated from one another. I know this is a simplification because there are also inter-process communication mechanisms that allow cooperation between processes, but for the aim of the talk is enough to think about processes as isolated entities that runs in ring 3. They use the operating system to interact with hardware devices, as I said, with explicit APIs. The OS schedules the execution of these processes, so it has an internal scheduler to execute these processes. And in general, the operating system acts as a filter for the request coming from userland processes. So before accessing to hardware on behalf of the processes, the operating system will perform like a sanitization of the parameters that comes from processes from userland. This is the revised scheme when we introduce an hypervisor inside the software stack. So in this case, the operating system is replaced with the hypervisor, or also known as the virtual machine monitor. In Ring 3, we have different operating system that runs on the same physical machine. So this is just a higher level of perception compared to the previous one. And this higher level of abstraction allows us to execute multiple operating systems on the same physical machine. Here, there are the same properties that we saw earlier that applies also for a virtualized environment. Only the agents are different. So in this case, we don't have processes inside in Ring 3, but we have full systems known as guest operating systems that are completely isolated from one another. And they use the VMM, the hypervisor, to interact with the hardware devices. Instead, in this case, the mechanism is not explicit, so they do not use an API, but we will see later how they can interact with the hypervisor. And the VMM also contains a scheduler for the execution of different guest operating systems on the same machine. And also, in this case, the hypervisor is acting as a filter for the request that comes from the guest operating systems. So the first question that can come up in your mind when we saw this scheme is we saw earlier that the operating system, when it runs at Ring 0, can access directly to hardware devices because it has the privilege to do that. But now, since the operating systems are running in Ring 3, how can the operating system, the guest operating system, access hardware if they are in Ring 3? Because in Ring 3, this operation should not be allowed. Well, they use an implicit API. That is, the guest operating system will try to execute hardware devices as if it were on bare metal, so like in a normal scenario. But of course, if the guest operating system is running in Ring 3, so this operation is privileged, and this will cause a trap. When the hypervisor is installed onto the machine, the trap handler for these operations is set to a routine inside the hypervisor code that will manage these requests. It will decode the type of operation that the guest operating system was trying to perform, and if the parameters are valid, so it is a valid request from the guest operating system, it will emulate the operation for them, and it will return the expected result in registers or in the memory of the guest operating system as if the operation was executed on a real hardware. This is the trap and emulate technique, and this is a generic implementation that all hypervisors uses, with a few exceptions, but is out of scope for this talk. This is the architecture of VirtualBox. So we are now going into the specific internals of VirtualBox, that is the target that I use for my exploitation. As we can see, is a sum of multiple modules running both in Ring 0 and in Ring 3 of the host operating system. For the purpose of this talk, there are just a couple of modules that are interesting for us, that are the VBoxDD, both in Ring 0 and in Ring 3. And in these modules, there is all the code for emulated hardware devices. So for 90% of the code we will see later is inside these modules. Then we have the VBoxRT, also in Ring 3, which is just a module that contains runtime helper functions, for example, for allocate memory or some wrappers around traditional functions such as memcopy and memcompare. We will use that later. Then there is, of course, VirtualBox.exe, or the analog one with in Linux, that is just the front-end GUI that the user can use to set different parameters of the guest operating system that they are trying to execute. And on Windows communicates with the core hypervisor using COM, instead on other operating system use XPCOM. So during boot time of the guest operating system inside VirtualBox, there is a component called the pluggable device manager, which is responsible of instantiating all the fake hardware devices that the guest operating system will see after the booting of the machine. And I don't know if it's readable, but I will go through a little bit. So we have a for loop, which is just iterating through all the devices that the guest operating system needs that can be configured with the front-end GUI. And for all of them, we'll allocate some memory for a C structure that represents the fake hardware for the guest operating system. This is used by the hypervisor to manage different settings for the same hardware devices for different guest operating systems. And in this case, we are taking a look at the Ring 3 initialization of the pluggable device manager, but if there is also the need for the Ring 0 initialization, it will issue an IOCTL call to the Ring 0 device driver to initialize also the Ring 0 part of the device. So, in general, when an operating system, but in this case, in VirtualBox, we're talking about guest operating systems, they try to access hardware devices. During boot time, they know the base address of some memory that can be used to access internal registers of device drivers, or using I/O ports with specific assembly instruction that we are going to see in a minute. And using the memory mapped I/O or the I/O ports, they can interact with the device. In this case, the device they are interacting with, they are not real because they are faked by the hypervisor. So in this case, there are some functions that we'll use as a callback to handle these accesses to specific memory regions. In this case, in this image, I've copied the code for the m0le handle for read and write operation for the E1000 Internet controller that we will see in a minute. And when we interact with this code, we are just in the guest operating system. We are just mapping the address of the hardware device we want to access, using, for example, IO remap as a function on Linux, or on Windows, the mmap IO space. These functions returns a virtual address, kernel virtual address, that the guest operating system can use to access the internal registers of the hardware device. Instead, for I/O ports, we have the in and out instructions with different variants, which basically just the size of the reader or write operation to access the I/O ports on the same device. This is the generic IO m0le handler. So this is the first layer that is going to be executed when an m0le access is executed on the guest operating system, and then this function will dispatch the correct m0le handler based on the address that is going to be accessed. Okay, so regarding the E1000 controller, this is a PCI device, so it is exposed through the PCI bus. And this is, for example, is the function routine on the Linux kernel to walk the PCI bus at boot time to understand what devices are connected to the PCI bus and to initialize the driver specific for that specific hardware device to handle the communication with the hardware device. And as we can see, in the PCI bus, both addresses of m0le regions and the I/O ports are defined. So at boot time, the guest operating system knows the memory regions for the specific devices. In this case, we are inside a guest virtual machine in a VirtualBox, and using the Linux command ls-pci, we can see all the devices that are discovered by Linux at boot time. And as we can see, there is also our Ethernet controller here. And we can see also the memory region that this device exposes to the kernel. We can see that there is a memory region, a m0le region, and also some I/O ports. We can also see the device driver that is responsible for communicating with this device, which is the E1000 driver. As I said earlier, there are different registers that can be accessed, in this case in the E1000 controller. There are quite a few. And of our interest are this one, since we are going to discuss the transmission side of the E1000 controller. We have the transmit descriptor based low and high. We will see later what they need. And also the head and the tail for the transmit descriptor. Inside the documentation for the E1000 controller, there are also described some packets. In this case, are transmit descriptors that are used from the guest operating system to communicate with the controller. So the operating system does not directly send the data of the frame that you want to send out of the network, but instead communicates using these descriptors that can be used by the E1000 controller to then get the actual data from memory through DMA, which is direct memory access. In this case, we have the context descriptor, which is the first type of transmit descriptor that we can find in the documentation. And also, there is a data descriptor. Data descriptor contains a pointer to the actual buffer in the memory that contains the data of the packet. A packet descriptor, in this case, is just the sum of a context descriptor and a variable number of data descriptor based on the length of the packet that we want to send. And the last data descriptor has to have the end of packet flag set to 1, just to signal the E1000 controller that this is the last descriptor for this packet, so that it can process to analyze other packets. So this is the structure of a packet. We have a context descriptor that describes the whole packet, and then each data descriptor for each segment of the packet that we want to send. So the generic operations that a 1000 driver should do is to allocate some memory for this queue that we will see here. Yeah. So this is some memory that the kernel of the operating system has to allocate to insert different descriptors that you want to send. And then it will set the TBL and the TBH with the physical address of this transmit queue in the kernel. And then it will set the head and the tail at first equal to 0 while filling up this queue. And after that, it will set the tail to the end of the transmit queue, so to the next chunk free inside this queue. When the E1000 controller see that the TDH and the TDT are not at the same value, it will start fetching all the transmit descriptors that are between the head and the tail, and after that, it will update the head to signal the software to the operating system that all the packets were, that all the descriptors were parsed, and so they can be considered sent. This is the VirtualBox implementation for what I've just described. So this is the E1K reg-write TDT. This is the function that is called when an update to the transmit descriptor tail happens in the guest operating system. So we can see that there is a if condition to check if the head is different from the value of the tail. If that's the case and the E1000 controller is up, so it's running, then the E1K xmit pending function is called to process all the transmit descriptors that are between the head and the tail. At first, when these transmit descriptors are parsed, the first one that goes through parsing is the context descriptor, because this is a per packet descriptor. We need first to update the context to parse the other data descriptor that will follow. So in this case, we are just updating some structures inside the greater structure of the E1000 controller, just to make sure that we have the maximum segment size, which is the maximum allowed length for that packet, so that that data descriptor can be handled correctly. After that, all the following data packets are parsed. In this case, we can see that there is a switch case, and if the packet is of type data descriptor, if the packet is not empty, so it does not have a data line equal to 0. The data descriptor is parsed using the E1K fallback add to frame, which will just add to the current frame we are building this new data descriptor. And here we can see the logic of adding existing data, the new data descriptor to an existing packet that we are building. So at first, we are using the CB variable, which is a uint32, to calculate how many bytes we are left in the current frame we are building. If we have enough space for the data descriptor we are parsing, then we can add that to the current frame using the E1K fallback add segment function. This function will use this other function, which is the PDM dev helper physical read, which just reads a guest virtual address, and it will store the result, in this case, inside the ATX packet fallback buffer, which is allocated onto the heap inside the E1000 structure. And we'll use the U16TX packet len variable to handle at the offset inside this buffer to append data to. If this is the last packet, the data descriptor is the last data descriptor that we are parsing, then we will proceed into the transmitting phase of the actual frame we've just built using the E1K transmit frame function. And this is from the left. So here we can see that if the packet, if the packet is basically sent using a callback to the actual driver that is responsible of sending the data to the network. But if there is a condition here at the bottom, that if the loopback mode is enabled, which is just a flag in one of the E1000 register, if the loopback mode is enabled, this packet is not sent to the network, but just retransmitted to the receiving side of the E1000 controller. And for that, the packet is just copied using a memcopy to this static buffer, which is the RX packet inside the E1K handle RX packet. Now, let's gonna talk about the vulnerability I used for this project. I used an old vulnerability, which is CVE 2019-2722, which does not have a public exploit. We can see also that the description is pretty vague, because there is also no reference to the E1000 controller. They just say that there is a vulnerability in the core component of VirtualBox without any other details. So this is the state. These are two packets that we have to send to trigger the vulnerability. I'm gonna walk through the parsing logic for these packets to see actually where the vulnerability lies. So at first we have a packet with a context descriptor with the maximum segment size of 0x10. So this is the maximum allowed length for a data descriptor that will follow. Then we have a first data descriptor with a size of 0x10. And then a special data descriptor with the size equal to 0, but also with the end of packet flag set 1. After that, we have another packet with the context descriptor with the maximum segment size, which is less than the first maximum segment size, and then we will have a variable number of data descriptor. So let's see how these packets are parsed by VirtualBox. So at first, we saw that there is, of course, the updating of the context descriptor. So in this case, of our interest is just that the context descriptor updates the maximum segment size, so it will be 0x10. Then the data descriptor of the first packet are parsed. So we come back to this function, the E1K fallback add to frame function, which will just check if we have enough room for inserting this segment inside the current frame. In this case, it is. So we are just adding this data descriptor to the current frame, and we are updating the U16TX packet len variable, which will contain at the end of this process the value 0x10, because this is the number of bytes that we've just appended to the current frame. Okay. After that, we will have to parse the second data descriptor, which has a size 0 and end of packet equal to 1. But we saw earlier that if the size is 0, the packet descriptor is skipped. So in this case, it's skipped, and since there is also the end of packet flag set to 1, the VirtualBox will consider this packet completed, already transmitted, and so it will start parsing the next packet, which will contain a maximum segment size of OXE in this case. So at first, there is also the update of the context descriptor, so the maximum segment size will be set to OXE. And after that, we will come back to the E1K fallback add to frame function to insert the first data descriptor. In this case, we have an arbitrary size. And one important thing that we have to remember is that the U16 TX packet length will still contain the OX10 value, because when the previous packet was completed, this variable was not resetted. So in this case, U16 TX packet length still contains OX10. And since we control the U16 max packet length, because it comes from the maximum segment size that we can control with the context descriptor, we can cause an integer underflow in the CB variable, because we can set a U16 max packet length of less than OX10. So when there is this subtraction to verify that we have enough space to add the segment to the data frame, will cause an integer underflow. And since this variable is a uint32 size, is unsigned, so this variable will take a huge value, unsigned in this case. So this will allow us to copy more data than the maximum allowed inside this frame. And since at first the data are copied inside the heap buffer, at first we have the heap overflow coming from this integer underflow. And as we saw earlier, if we also set the loopback mode, we turn on the loopback mode, we will also copy this data inside a static buffer, basically allowing us to copy an arbitrary data beyond the maximum allowed size for this static buffer. So yeah, surprisingly enough, VirtualBox by default is not compiled with Canary, at least this version. So we have directly RIP control over this function. When this function, the A1K handle RX packet, is called with the arbitrary size data descriptor, we can control the return address for this function, and we can redirect control flow execution. So yeah, basically we are done, right? So we can just insert shellcode inside the stack and execute that, right? Well, actually no, because we are not in the 90s anymore. So we need to come up with some strategies to bypass mitigations. Yeah. First of all, we have ASLR. So we don't know where we are in memory after the corruption of the stack, because there is this randomization of the virtual address space. And also we have NX or DEP on Windows. So even if we allocate some shellcode into the stack, we can go back and execute that onto the stack. So at first we need an ASLR bypass to actually know where we are. So in this case, we can use the heap overflow I mentioned earlier, because at first the overflowing packet is copied into the E1000 structure onto the heap. So from there, I won't go into much detail because it will take a long time, but we can use the data-only attack to extract an address of a static string that is allocated into the heap. And from there, since one important feature of the VirtualBox heap is that the structure are always allocated at the same offset. I think it's just done for some performance overhead, I think, so that they can obtain pointers to important structures in a quick way. So if we leak the address of this static string, we can obtain the base address of VBoxDD, which is the module in which our code is executed. And with that, since we have NX enabled, we have to write a custom ROP chain to actually execute some code using gadgets that are already present in the executable. So this is the code for the exploit regarding the leak part. So we are just using the leaking technique to get the VBoxDD base. And with that, we can also get some other interesting addresses, such as the address of the buffer of the frame, so the ATX packet fallback, that we can use later to just use as a temporary buffer to copy shellcode somewhere else. So regarding the ROP chain section, we can use all the gadgets that are inside the VBoxDD module. In this case, I just built an arbitrary read gadget that will just sum of other smaller gadgets. And with that, we can use this arbitrary read to read interesting pointers on Linux from the procedure linkage table, which is just a table of functions that are imported from other modules. And on Windows, there is the same concept with the import address table. So using that arbitrary read gadget, we can read an interesting function that is present inside the VBox RT module that we mentioned earlier, which is RT memexec alloc tag. This function will happily allocate some memory for us with read, write, and execute privileges, and it will return back a pointer for us. So basically, we can use the packet that we control. We can also have the pointer to this packet onto the heap. We can place here the shellcode, and then copy that into this newly allocated executable page. And then we can jump to this executable page to execute our shellcode. This is the screenshot from WinDebug after the execution of the RT memexec alloc tag function. And we can see with the bang heap command on WinDebug the privileges of the newly allocated heap page. In this case, we can see that there is the page execute read write permissions. So we can copy shellcode there and also execute that. For the Windows exploit, because I wrote the exploit both for a Windows operating system, host operating system, and also for a Linux one. So for the Windows shellcode, I'm just using a traditional shellcode, nothing pretty interesting here. So I'm just taking the pointer from the thread environment block, which is at GS segment plus OX60. And from there, we can get the list of modules that are loaded in memory for this process. And we know that the fourth or the third, I don't remember, but is at the static number. We can get the kernel 32 base address from this list. And we can use that to call the winexec function, which is a pretty handy function that will happily execute whatever we pass as the string argument. So in this case, I'm using calc.exe to execute, to pop a calc to the host operating system. For Windows, for Linux, the things are pretty easier because we can just manually execute syscalls without problems. So we are just forking the process of the hypervisor to get a new process, and then execute, in this case, just a terminal. Okay, so we have demo time. So let's see. Okay, this first one is for a Linux host operating system. A little bit of context here because I think it's pretty messy here. Because I've used the Nexterd virtualization to build this environment. So the host operating system is running under QEMU, and this case is a Linux operating system. And inside it, I use the VirtualBox to run another virtual machine, in this case a Ubuntu machine, where actually the exploit will be executed. So I will start executing it, okay. So here I'm using a bash script to just removing the E1000 traditional driver, just to don't have to deal with concurrency issues writing to the E1000 registers. So I'm removing that and also compiling the exploit, of course, which is just a Linux module that will be inserted at runtime. Okay, so we can see here that the E1000, okay. And here we can see the shell being executed onto the host operating system. Okay. The same here. In this case, we are executing a host operating system which is Windows under QEMU as well. And inside Windows, we have a VirtualBox instance with a Ubuntu machine, also in this case. And also here, we are just removing the E1000 driver, which is the standard driver. And now I'm going to insert my exploit, always as a Linux driver. And we should see a calculator spawn, yeah, here it is. A calculator spawning on the host operating system. Also here, I've also managed to achieve process continuation, which is the fact that the virtual machine does not crash. This is basically because all these events inside the virtual machine are handled in a loop, so we can just jump after the corrupted stack we used for the drop chain, and we can come back to this event loop, and the virtual machine will continue executing fine. So we come back to the slides. Okay. So we saw the Linux one, also the Windows one. Yeah. And yeah, we have achieved VM escape. We can execute code into ring 3 of the host operating system. Further analysis can be done to exploit more this vulnerability to, for example, leverage some VirtualBox driver inside the host operating system to do a privilege escalation. But for now, we are just fine with ring 3 execution. Thank you.
So, thanks for your talk. It was really interesting. I was wondering, have you ever done some experiments on other hypervisors? And if yes, have you ever dove into para-virtualization? I mean, para-virtualization, the way I see it, as far as my understanding goes, is a way of just talking to the hypervisor and, syncing so that you are not supposed to see this happening, like this handling, this very complicated one. So, for curiosity's sake, have you ever experienced some attack with para-virtualized systems? And what have you discovered?
Yeah, well, actually, I'm experimenting it right now because I'm taking a look at Hyper-V, which is the hypervisor implementation from Microsoft. And yeah, they use para-virtualization a lot. And yeah, from that point of view, the idea of para-virtualization is just to have a standard interface that all devices can use to communicate with the hypervisor. Of course, the guest operating system needs to know that is under virtualization, of course, in order to talk with the hypervisor. But yeah, this is the general trend. So all the modern hypervisors are trying to go away from this legacy implementation for emulated device because, for example, I've mentioned that earlier, that in this case, all the code that is inside the VirtualBox for handling this device comes from the standard implementation, the specification of Intel in this case, which is the main manufacturer of this device. So in this case, VirtualBox has to manage all the devices that can be inserted into the guest virtual machine. So there is no standard API, for example, or a protocol to communicate with the hypervisor. And so for example, each developer has in the VirtualBox has to implement a specific driver, a specific implementation for that specific device. And of course, this can lead to some edge cases or things that in the real hardware devices works perfectly fine, but in the implementation there are some mistakes or something like that. So yeah, the trend is to go with para-virtualization. So yeah, it's something that if you're interested is worth analyzing because it will be the standard from now. Yeah.
Thanks a lot.
Hi, so I'm interested in how did you actually find the bug after this only very brief description of it?
Yeah, so basically just doing diffing around with the code base of VirtualBox. And actually there is the ZDI description for this vulnerability, and they also mentioned the E1000 in some way. So it's a little bit more clear than this description we saw. But yeah, basically just doing diffing on the E1000 file, because I think that VirtualBox, the VirtualBox developers did a great job into dividing the source code of VirtualBox so that it's pretty easy to find a specific device implementation for that device you are targeting. So by diffing the older version with the newer one, I saw that they added this reset variable that we saw here. I will try to go back to the slides. Basically, when there is the check, if the data len is equal to 0. So, okay, here, when there is the E1K log2, after that they added a line to just reset the U16 TX packet len, because actually this is the bug, so that when another context descriptor for another packet is parsed, there is no this issue anymore. Yeah.
Okay, thanks.